All right, well, first off, I'd like to thank ILSI and CNS for the invitation to speak today. And for the next few minutes, we're going to shift gears a little bit. We're going to talk not so much about dietary patterns and talk about Canadians as a population. Rather, what we're going to look at is what's the evidence out there that suggests that we can personalize diets. And this is the idea of personalized nutrition, or as some of you may have heard, precision nutrition. The first thing I want to just say is I have no actual or potential conflicts of interest. So let's talk a little bit about general dietary recommendations, because ultimately when we're talking about precision nutrition or personalized nutrition, we're not talking about something that's going to replace these general recommendations. What we're talking about is, can we fine-tune them for the individual? So these general population-based research findings that have driven and allowed us to establish these recommendations, they are an absolutely necessary starting point. And they are a starting point for not only the Canadian population as a whole, but if we start to look at the idea of personalized nutrition, this is the foundation on which we will build. And so there's panels out there that look at the scientific literature, they will look at the evidence that's out there, and then they will assess the quality of that evidence to see how robust it is and how strong that evidence is. And they will look at basically these associations between diet and health. And so we get to these types of things that sodium, high levels of sodium are associated with increased risk of high blood pressure, or increased consumption of trans fatty acids is associated with an increased risk of cardiovascular disease. And that dietary patterns, things that we've learned about already today, characterized by higher consumption of things like vegetables, fruits, whole grains, and lower consumption of red and processed meats, sugar-sweetened beverages, etc., that these are associated with positive cardiovascular disease outcomes. So these are the types of things that we're working with. And the reality is that allows us to build a fairly simple model, is that we have a nutrient or a food, and that is associated with a health outcome. But the idea of personalized nutrition is going to take this a little step further and fine-tune this a little bit. So what we really need to think about then is that population-based advice that we are given, does that work for everybody? And there's an excellent article, a review article that was just published by Drs. Wang and Hu from Harvard University, and I think they very eloquently said what we are going to talk about for the next few minutes. Current dietary recommendations are based on population averages and often do not take into account individual variability in response to nutritional components. Although successful in reducing the population-level chronic disease burden, dietary guidelines based on population averages may not be best suited for a given individual. So intuitively, I think we all know this, that some individuals are going to respond to a certain food or diet in a certain way, and other people will respond differently. But how do we actually take that anecdotal evidence that we have, because we all have friends that respond in different ways to the things we eat, how do we take that and actually translate that into science evidence? And so just to give you a couple of examples. So this was a study that back in 2008, it was actually one of the first studies that showed individual responses. And of course, when we're thinking about population-based guidelines, what really we're going to be reporting the data as are averages or means. And that's what this is showing here. So this was a study where basically what they did, it was a study run in the UK in men that were 35 to 70 years of age. And what they did is a 6-week intervention with a fairly high dose of omega-3 fatty acids, EPA and DHA, so 2.5 grams per day. And what's known with that is that a high level of EPA and DHA on a daily basis has been reported to increase slightly LDL cholesterol levels. And so that's what I'm showing you here, is that's the mean response that was noted in this group of 74 individuals. However, the reality was, this is how each of those individuals responded. You can see there's a huge range in the types of responses. There are people who have had reductions in LDL cholesterol, there are people who have had no response whatsoever, and then there are people that have had increases. So when we're showing and reporting those means, while they're very useful to sort of synthesize a clear message, the reality is that people are responding very differently. Now, it doesn't matter what nutrient I take and what health output I would talk about, the same type of thing has been shown So here's a second example. And this is some preliminary data in collaboration with Dr. Peter Jones, where what we've basically just simply depicting here is the change in blood glucose in response to a 6-week consumption of traditional canola oil. And again, you can see each bar represents an individual. You would think it's the same data I just showed you. And what I'm just showing you there, which you can see with the average change, that's the average of those 106 individuals. A very minor, statistically insignificant reduction in glucose response. So you look at this and you realize that there's different subsets of the general population that can be categorized. And we can categorize them in this way. As responders, so these are the individuals that would respond to the intervention in the way that we would hope to see. In this case here, it is a reduction in blood glucose levels. We have our non-responders, people who simply just don't respond to whatever the intervention is. And then we have our adverse responders. This is sort of the unexpected response. What we're not expecting to see or anticipating to see, this is the people that respond in the opposite way. And again, I could take any nutrient and show this type of individual data, and you would see that there are differences in how these people will respond. So this is what the idea of precision nutrition or personalized nutrition is going to go and tackle, is these individual responses. We obviously now know that it doesn't always work in the way we anticipate. So what exactly influences this relationship between a nutrient and or diet and a health outcome? So if we took that simple model that we started off with before, which is what we use to create these dietary guidelines, the reality is it's a lot more complex for when we take it down to the individual level. And in fact, what we have in there are all these other factors that introduce variability. So you can see here that that relationship between nutrient or food and a health outcome, there's a lot of intermediates in there that can affect why and influence why a person might respond differently. So there's certainly things like lifestyle behaviors, so dietary patterns, exercise habits, whether they smoke, the kinds of medications they're taking, and so forth. Gut bacteria, our gut microbiome differs very significantly from person to person. That influences how we digest and absorb foods. So that's a factor that can influence how foods will get into the body and therefore affect the underlying biological framework. And that's what that third panel is showing, is there we know there's genes, proteins, and metabolites that will respond to those foods, and that will actually form a network. And that's what you're looking at here. These genes, proteins, and metabolites connect together to form a very complex biological network. So we can see that all of these different variables influence that relationship that take us from nutrient to health outcome. And so we can very quickly see that from an individual perspective, there's a lot of opportunity for variation in the population. So I'm going to focus purely about genetics today. And this is really, when we talk about precision nutrition or personalized nutrition, the area of genetics is really where it's at. This is the hot area of research. This is the hot area in terms of direct-to-consumer companies that exist out there, and I'll talk a bit about them later on. But what we really know is that genes influence how people respond to foods. And that premise is really the underlying notion for precision nutrition or nutrigenomics. So nutrigenomics is really the science that underlays this idea of precision or personalized nutrition. So what exactly is nutrigenomics? Well, at its very simplest, nutrigenomics is a study of how nutrients interact with our genes to influence health and disease. Okay? So when I said nutrigenomics is a hot topic, I'm definitely saying this objectively, although I obviously am a little bit biased in this area, but I am saying it objectively, that if you go onto the internet and you type in nutrigenomics or personalized nutrition or precision nutrition, you are going to have thousands, hundreds of thousands of hits. You're going to get things like different companies out there that are selling their products. You're going to get blogs about personal experiences, and you're going to get just a lot of information. There's a lot of science out there that is really hammering home this point that nutrigenomics, personalized nutrition is an important thing. And so I've just captured a few of the different sort of nice images that caught the notion of nutrigenomics. And I like a few of them here. You know, the answer may be in your genes. You are an individual, singular, unique, eat like it. So these are the types of messages that people, when they go onto the internet, that's what they're seeing when they type in precision nutrition or nutrigenomics. So what exactly can nutrigenomics offer us? And to be honest, this is not an extensive or exclusive list of all the different benefits that we can have. But I just wanted to touch on a few different areas that can really be advanced thanks to this understanding of nutrigenomics or diet-gene interactions. So understanding how nutrients influence our genes and how they interact with our genes will improve various things. So for example, understanding taste preferences. Why do some people prefer the taste of certain foods versus other ones? We now know that there are taste receptors, and in those taste receptors, there are genetic variants that influence a person's preference for different kinds of foods. Food tolerances. Why do some people have a reaction to food and others don't? The classic example is lactose intolerance, and of course that comes down to a gene, and there's variants in those genes that influence a person's sensitivity to lactose. Nutrient bioactivity. So this is really the key, right? As we consume foods, those foods contain nutrients, those nutrients get into our bodies. So we have to think about all the different biochemical pathways that influence that. The idea that they have to be digested, absorbed, metabolized, and stored, and then released in times of need. All of those are controlled by biochemical pathways. Those are underlying that, and underlying those pathways are genes that can have variants. So people can be more or less able to move these things around the body. And then finally, the big one, of course, is health outcomes, is understanding why some people might experience an improvement in a particular health outcome while others experience the opposite, this adverse effect. So these are just a few of the areas that are advanced by studying diet-gene interactions. And so now if we go back to our general model here, nutrients and their association with a health outcome, what we now know is that that's actually not accurate for the individual. That rather, what we know is that nutrients can interact with genetic variants, and those genetic variants can then influence a person's response and ultimately how that outcome that they're going to experience. So at its simplest, for every person in this room here, is that there are 3 potential genotypes that can exist for any gene in our body. And I just simplified this as genotype A, B, and C. But you can kind of see here that I could throw out 3 different paradigms of that in response to that nutrient. That some people might improve, some people have no effect, and some people worsen. Again, highlighting that data I showed you at the very beginning. So this idea that one size fits all may not actually be very accurate. One size fits most, but probably not everybody. So before we go on, just to make sure that we're all on the same page, when we talk about genetic variants, there's lots of different variants that exist within our genome, but when we talk about nutrigenomics or personalized nutrition, what we're really talking about are the science of single nucleotide polymorphisms, also known as SNPs. And so these SNPs are spread throughout our entire genome. And this image here sort of illustrates that we're talking about a very specific location in our genome where it would vary between any 2 individuals, just with a single base nucleotide in our genome. Now, when we say that people are 99.9% genetically identical, that sounds impressive, but given the size of our genome, that still means that there's upwards of millions of SNPs that can vary between any 2 individuals. So there's a lot of opportunity to have variability between different individuals. That's something to keep in the back of our mind. There's a lot of variability that exists. So given this foundation that we're going to look at single nucleotide polymorphisms, let's look a little bit for the next couple of minutes at some of the scientific evidence that exists that really shows that there is research out there that supports this notion that genotype can influence response to nutrients and foods. So we have to look at a couple of different things here. And I like this slide because it's essentially about putting these different puzzle pieces together. We know that diet and genes are going to interact. We know that diet genes will interact to affect health. But ultimately, knowing all that information is wonderful, but if it doesn't do anything, if we can't change behavior. And that's really what nutrigenomics is the biggest challenge facing nutrigenomics is how can we take that information to ultimately change a person's behavior. So first, let's talk about a couple of the science examples here, the research that's out there that shows that there is some basis to this idea of personalized nutrition. This is an example by colleagues at the University of Toronto, Dr. Ahmed El-Sohimi, and it's an excellent example. It's one of the first that's really, that came out that was really a strong example that's now being independently reproduced in the literature, so it's a very strong association. And essentially what they were looking at here was the relationship between coffee and genetic variants in a gene known as the CYP1A2 gene. This gene is responsible for the breakdown of caffeine. And they were looking at its relationship with cardiovascular disease. Now, the association between coffee intake and cardiovascular disease is actually a little bit controversial. And this is another area where nutrigenomics can help to kind of clear the messages. Is that controversy that exists because of the populations that are being used being genetically dissimilar? That creates an interesting sort of thing that we can think about as we move forward. But anyways, back to the point here is that caffeine is broken down by the CYP1A2 enzyme. And there's a variant in here that's given at the bottom left here by its unique identifier. There's a variant that exists that's been reproducibly associated with the breakdown of caffeine in coffee. Now, this is actually an important variant. You can see here that 37% of the population carries this, what we refer to as the rare version of this gene. But as you can see, 37% doesn't really make it very rare at all. So what do we have here? We have coffee that interacts with this CYP1A2 gene, and we have our 3 different genotypes that exist. And what you can see here is those 3 genotypes have been associated with the breakdown of the caffeine that's in coffee. So we have a genotype that has a fast breakdown. This is the AA version of this gene, and this is the more common or prevalent version of the gene. But then we have our heterozygotes and our minor allele carriers that are collectively going to be grouped as rare versions of this gene, the AC and CC, and these individuals have a slow breakdown of that caffeine. So what the researchers wanted to do is they wanted to look at the relationship between coffee intake, cardiovascular disease, but based on this genetic variant. And so what you can see here is this was a study that was conducted in the Costa Rica heart study population, about 4,000 individuals. And what they did is they went back and they looked at their population and stratified it based on their genotype. So the AA genotype are the individuals that are the major allele or the more common version of this gene. And you can see here that based on the white to the lighter gray all the way to the dark bars is basically increased amounts of coffee cups per day, with the black being the black bar corresponding to 4 cups a day of coffee and more. And what you can see in the AA individuals, the common version of this gene, is that essentially there's no real effect on cardiovascular risk. If anything, there might be actually a slight protective effect, but you can see that it's a little bit more random looking. The pattern isn't very clear. Where it becomes very clear is when you look at the minor allele carriers, these people who have the rare version of the gene. You can see here that with increasing cups of coffee, their risk for cardiovascular disease increases quite dramatically. So that means that individuals who have the slow breakdown version of the CYP1A2 gene, when it comes to the slow breakdown of caffeine, that this is actually associated with an increased risk of cardiovascular disease. Now, this is I found already interesting, but this was a study that followed up on this previous work that's very much hot off the press. It was published last month, and I actually really like it because it takes it to the next level. It looks at the role of caffeine that's being used as an ergogenic aid in sports, and so on exercise performance. And so this was a study that was quite small. It was done in 100 people, but they looked at the exact same gene. So again, the idea here is the same, is that you have your fast metabolizers and you have your slow metabolizers of caffeine. And what they've done is they've divided up their 3 genotypes along the bottom there in the figure. And essentially what they did is they looked at increasing amounts of caffeine given to these people on their performance during a stationary bike exercise. So people had to get on a bike and pedal for 10 kilometers, and they measured how much time it would take those people to do it. Now, of course, the idea being that if you have caffeine, this is an aid, this would actually increase your speed and therefore reduce your time in this particular study. And sure enough, when they look at the people who are the fast metabolizers, that's the AA genotype, what do you see? You see that the time is reduced. The more caffeine they consume, the faster they're able to perform this particular exercise intervention. Now compare that to the slow metabolizers on the other side, the CC variant. You see the exact opposite. Now I think this is a very fascinating and exciting sort of study because it shows that people are consuming caffeine with an intent that it's going to improve their performance, but the exact opposite is happening when they're actually consuming it, depending on their genotype. So this is the kind of science that exists out there that shows that there is definitely research highlighting that there is an interaction between genes and diet, or nutrients, or components of our diet, and some kind of outcomes. But the real question when it comes to nutrigenomics is, like, the research is great, and this certainly is what gets everybody excited. But the idea is, does this amount to anything? If we give this genetic information to people, does it actually change their behavior? It's all fine and dandy if we have this knowledge about these interactions, but it doesn't mean anything if we can't change people's behaviors. So we asked the question, does knowledge of personal genetic information actually change dietary behaviors? And so the first study I'm going to highlight here is actually a study that was conducted by my team, where we looked at dietary fats and whether knowledge of a particular variant that's associated and linked with dietary fat metabolism could change their uptake of dietary fats. So we're using our model here again, where we're looking at alpha-linolenic acid. And we know that alpha-linolenic acid can be metabolized within our bodies to generate a longer chain omega-3 fatty acid known as EPA. And EPA is an excellent fatty acid. It has anti-inflammatory properties. It reduces blood lipids, triglycerides, and so forth. So it's an excellent omega-3 fatty acid. We don't consume too much of that in the diet. Unless you have a high fish diet, you're not really going to be getting much EPA naturally. So this pathway becomes quite important for the average individual. This is where we take our essential fatty acid, ALA, and convert it into EPA. But there's a variant in the fatty acid desaturase 1 gene that is known to affect that sort of interconversion. And so what you can see here, again, using our model, is that we have people who are high producers of EPA, and then we have people who are low producers. And again, the low producers are what we would refer to as the rare genotype. But again, it's not so rare. 30% of the population has this rare genotype. So what did we do in this particular study? Well, it was a randomized controlled trial where essentially what we did is we had a small study group, 30 people in each group, but what we did is we had a genetic group and a non-genetic group. And essentially everybody got the same nutritional information. They all got the same information about omega-3 fats, where you could get them in the products and the foods, but the only difference was some people got their genetic information and others didn't. And so what we did is we performed this study in approximately 60 young female adults, and they were recruited for this 3-month intervention study. And so again, everybody received the same basic omega-3 info, but only half the people got their genetic information related to the FADS1 genotype. And what we looked at was a number of different things. We looked at both baseline and 3 months or after the intervention. We looked at blood fatty acid levels. We looked at omega-3 consumption in their diets using food frequency questionnaires, but we also performed other questionnaires looking at knowledge of that nutritional information. And to make a long story short, essentially we didn't see any changes in the 3 months in terms of, between the two groups with regards to blood fatty acid levels. But however, what we did see is that there was an improvement in knowledge and awareness in the genetic information group, the genetic group. So these are the people who got their genetic information. And we found that they had an increased awareness of omega-3 fat terminology. So there's a better ability to say, we understand the difference between ALA or alpha-linolenic acid versus EPA and DHA. They felt that the information, that basic omega-3 information that we gave them, allowed them to have a better context of their, was better understood in the context of their genetic information. And also, interestingly, they reported having fewer barriers to the consumption of omega-3 fatty acids, which of course are very expensive if you're going to get them through the natural sources of fish and so forth. So these were very positive short-term outcomes that we saw. And it suggests that providing individuals with their personal FADS1 genetic information could affect longer-term dietary habits when it comes to omega-3 fats. So as you can see here, in 3 months, we didn't see changes inside the body in terms of the blood fatty acid levels, but what we did see was changes potentially in the awareness and their knowledge. And this was really mirrored in another study here that was published in 2014, but they took it a step further, essentially, than what we had done, is they looked at both short and long-term effects of giving people personalized genetic information. So this was a study where what they looked at is they had 4 different nutrients of interest. They wanted to look at genes that are associated with caffeine, vitamin C, added sugars, and sodium. And each of those different components, there was a gene that's well known and documented to affect the levels in the body for those 4 different compounds. And they looked in young adults, and then they looked at food frequency questionnaire data, both at baseline, 3 months, and 12 months, to look at whether that genetic information actually created any changes in their dietary patterns. And what they found was very, very interesting. The first was at 3 months, they didn't really see much. So that aligns with what we saw. Really, at 3 months, you don't get much of a change happening. However, what they did see was at 12 months, longer-term benefits to giving people their personal genetic information. Now, they didn't see it with all the nutrients. Where they actually saw it was with regard to sodium. They didn't see anything in relation to caffeine, vitamin, and vitamin C, and so forth, but they did see an improvement in sodium. So what are we looking at here? Well, just take your eyes directly to the 12-month panel there. And essentially what they have is they have 3 groups here. They have their control group, so these are people who didn't get their genetic information. Then they have what they refer to as the intervention non-risk group. So those are people that have a variant, but it's not the risk variant. They're in the intervention group. They know that they have their genetic information, but it wasn't the risk variant. And then they have their intervention risk group. So this is the people who got their genetic information and they have the risk variant that's related to the sodium, related to sodium, which in this case was in the gene known as the ACE gene. And what you can see here is after 12 months, there was a very significant reduction in the sodium intake by these people. So people who knew that they had the risk aversion for this salt-related gene, they acted and reduced accordingly their sodium intake. So what this highlights is that there's potentially a longer-term benefit to giving people their genetic information. Now, this study here is a study that's ongoing right now, and it's probably the largest personalized nutrition study that's been conducted to date. It's known as the Food4Me Study, and this is a study that's being run in Europe. It's a European framework program across 7 different countries in Europe, and you can see there's about 1,300 men and women who are participating in this study. And the whole goal of this study is, does personalized nutrition have a benefit compared to standard population-based advice? And so what they've done is they've randomly allocated their 1,300 people into different groups. And you can see here there's 4 different groups. The first is the control group, and these are people who don't get their personal genetic information, but however, they are just given standard European population guidelines related to healthy eating. But then they had 3 different personalized nutrition groups, each of them becoming more and more personalized, if you will. The first one was simply personalization based on food frequency questionnaires. So everybody in this group would submit a food frequency questionnaire, and based on that, they would get tailored advice. The second level took that food frequency questionnaire and then added on top of that phenotypic data. So basically, they would know their blood cholesterol levels, they would know their BMI, and so forth. And then based on those parameters, in addition to the food frequency questionnaires, they would get personalized advice. The final level is taking the food frequency questionnaires as well as that phenotypic advice, and then adding on a third layer, the genetic information. So when we talk about personalized nutrition, I think this is a great example to show that personalization can become very, very precise, but it doesn't have to be simply genetics. We can talk about personalization as just being based on individual food lifestyle habits. But you can see here they've got these 3 different levels. So it really allowed us to tease apart the value of this phenotypic and genotypic data. And their primary outcome was really just looking at dietary changes after 6 months. So this panel here is a little bit overwhelming in terms of all the different bars and so forth, but what I want you to draw your eyes to is the bottom right figure, which is looking at the healthy eating index. And this is a good starting point to talk about. So the black bar corresponds to the control group. So these are people who basically did not get any personalized information. The next bar, that dark gray group, is the average of the 3 different personalized groups. The 3 individual personalized groups are represented by the light gray bars. And you can see there that the light gray bars, there's no real difference. And that's actually what they found, is that there didn't seem to be a difference in the different levels of personalization. As long as you personalize to some extent, you get a benefit. And that's what you see here, is that healthy eating index was actually increased with a personalized aspect that was given. And then what I'm just showing you here in the other panels are individual nutrients. So there was a strong reduction in saturated fat intake. There was a reduction in salt intake. There was a reduced consumption of red meat. So there's a number of different parameters that were more strongly impacted as soon as you personalized the advice you gave these individuals. So what did they conclude? At the end of the day, what the authors concluded is that personalized nutrition advice was more effective at improving dietary behaviors when compared with conventional one-size-fits-all population-based advice. However, they did say there was no evidence that including phenotypic and phenotypic plus genotypic information enhanced the effectiveness of the personalized nutrition advice compared to individual dietary intake alone. So it shows here really that as soon as you personalize diets even a little bit, you get the benefit. You don't necessarily need to go to a phenotypic or genotypic level to get those benefits. And this is reflected by a systematic review that was conducted several years ago, where they really did a meta-analysis to look at the impact of giving people or communicating genetic risks related to three different parameters. One was diet, the second was physical activity, and the third was smoking. And the authors concluded these results do not support the use of genetic testing or the search for risk-conferring gene variants for common complex diseases on the basis that they motivate risk-reducing behavior. But, and this is actually the key point here, because this sounds like I'm going against everything I just said, but the but here is nutrigenomic information may be used to inform behavioral recommendations which are highly specific and targeted. So what they actually found is that when it came to physical activity and smoking, genetic information really didn't do too much. But where they saw significant changes was with regard to dietary behaviors. If you give people genetic information related to specific dietary components, that can actually have very strong beneficial effects. So where do we go from here? Because clearly the data that exists right now from a research perspective is becoming more and more robust. It's being reproduced by researchers around the world, and this is a good thing. This is what the field definitely needs. But there's still the question mark about translating that to people and affecting behavioral change. So where do we need to go? Well, we definitely still need more research in the area, and there's a number of questions that remain unanswered to date. So for example, are specific subsets of the population going to respond differently to personal genetic information? So there's no real studies out there that have really tackled this question. Do young versus older adults respond differently to that type of personalized information? What about men versus women? Most of the time, all of this is just being amalgamated into these population-based studies and not being teased apart in those sort of subsets of the population. Are behavioral changes sustainable? So I think some of the data that's now starting to come out is showing that if you go longer term, you're going to have sustainable changes. Short-term studies of 3 months or less probably aren't going to get any significant data out of them. But if you start going into 6 months and more, you might actually start to have reproducible changes that are actually sustainable. One question that hasn't been looked at, and this is particularly relevant because now there's these direct-to-consumer companies that exist, is can we overload people with too much genetic information? In all of the studies I showed you here, people have been given information about 1, 2, 4, 5 genes. But if you look at companies like 23andMe, these are companies that are giving people 60, 70, 80 genes worth of information back. That is overwhelming as amount of information. How do people actually take that information and translate that into an action plan? So we need to sort of understand, is there a sort of a maximal level of genetic information that we can give people? And then finally, what's the best way to communicate this information to people? So we certainly know that individuals like going to family physicians to get their health advice, but there's dietitians and there's academics as well that have been identified as groups that are important to communicate this type of information. And then how we deliver it. Is it in person the best way to do it? Now there's more and more movement towards phone-based apps to deliver information. How does that work in comparison to the in-person information? And then of course the internet, as we heard before, which is we don't really want to go there to get that information because that's full of personal anecdotes and not particularly necessarily the right information to give. So we are faced then, as a field, with a very major challenge. And underlying all of this, there's a huge, huge, huge challenge: human nature. We can't beat it, really. People will respond differently to receiving personal genetic information. And essentially, you have three outcomes. There's a positive effect. People will do something about it. They get their genetic information, they feel motivated, they feel empowered, they make changes to their diet or their lifestyle. Then you have the negative effect. People get the information and they say, this isn't good, I have all the risks, I can't do anything about it, I might as well just give up. And that's obviously the population there that we want to intervene with. We want them to change their mentality because that's the people that will have the greatest benefit. And then there's the third group of people who will say, this is interesting, but I'm not really going to do anything with it. I'm not going to change my behavior. So you can see that this is ultimately the major challenge that is facing the field of personalized nutrition. Now, while we recognize this, there are companies out there that have just leaped ahead and are now offering this type of direct-to-consumer testing that you can send in your DNA and you can get this type of information back. And I'm only highlighting a few here because there's a lot of companies that exist out there. But I want to highlight the fact that not all of them are focusing on necessarily DNA and genotype. So for example, at the top here, you have a company, most of these companies are based in the US. You have a company named Care Of, and they offer personalized vitamin packs. So based on your genetic information that you would send them, they will then tell you what kind of a profile of vitamins you should consume. And you can see they even send you a little package that would say, hi, this is so-and-so, this is what you need to have on a daily basis. A company named Habit was formed not too long ago, within the last year, and they've taken this to a slightly different approach where they look at how somebody responds to a standardized food intervention, and then based on that, coupled with genetic information, they provide action plan and meals that, that can potentially drive change. Nutrigenomics is a Toronto-based company where they look at genetic information related to diet and exercise. There's a company named Day 2 that was formed that looks very differently. They look at a person's response to a standard challenge, but based on changes or based on a person's microbiome. So in this situation here, they're no longer looking at genes, they're actually looking at gut bacteria as a predictor of how people will respond and personalizing interventions based on their gut bacterial profiles. And the last one here, which I put up here as a bit of a joke, but you can really get personalized tests for anything now. This company named Origin in the States, they also have a number of personalized tests, but I was particularly interested, if you're interested in knowing if you have what it takes to be a superhero, you even have the ability to know that through your DNA. They look at various genes related to strength and intelligence and so forth. I do not know if I'm a superhero or if I have what it takes, because Canadians unfortunately can't actually get this test done. But it just goes to show this is an area that is really active, and it's all about marketing in the area, getting the interest of people and so forth. But there's a lot of interest by the general population. So with that said, I'd like to just sort of thank, of course, the students in my lab who have really contributed to this work, and our collaborators as well, and of course our funding. I'd be happy to take any questions.
You have the floor. He's obviously a superhero. I have no proof of that. Thank you, David. This was a very elegant presentation, very clear, insightful. I guess one of the things I still struggle with is every risk factor has a different response to every nutrient. So we often plot these cholesterol response to omega-3, but then the insulin, the glucose, the blood pressure will have a similar pattern of response to every nutrient, basically. So what's the expectation to be able to deal with that amount of information and to make sense out of all of this?
It's a fantastic question, because all the research to date and the companies are really working on this very reductionist approach. One SNP affects a nutrient, and that's what's important. And you're 100% right. First of all, we don't consume nutrients, we consume foods, and we have millions of SNPs in our bodies that could be influencing different aspects of those foods. So that's a challenge that exists. And I think right now, where it's going is people are starting to recognize and create this idea of genetic risk scores, or looking at patterns of SNPs and associating those patterns with dietary patterns, dietary behaviors, and so forth. So it's essentially taking this sort of small, simplified data and trying to build it into more of a program where you can use machine learning tools, where you can create risk scores to try to get a better sense of really what the risk is. Because you're right, that is a major problem and a hurdle that we have, is how do we actually take it from the one gene, one SNP, all the way up to the foods. Yeah, thank you.